whether in free nature or whether in reality you could expect other points, say like on the x-axis 0.4 and on the y-axis also 0.4 and on the z-axis also 0.4, somewhere in the middle, you know, which is disjoint from all the other point groups.
You mean this?
No, somewhere in the middle where you have no points.
Ah, this.
Say 0.4 coordinate, 0.4 coordinate, 0.4 coordinate. Could you expect, or is it conceivable that you find aerosol particles in free nature which are, you know, in this range?
These results only come from the lab work, use standards.
Okay.
So only this 2 dots is from a hypha which is collected on Amazon rainforest. And the second one is we don't have much signals in this area in the middle because it's NH4 plus signals. It's I think it's very unique for amino and ammonium. So if the sample don't contain these materials, these molecules, they don't show nothing. It's there. So if they have something, it's really high ratio, more than 80% of the whole signal. That is why there's no signal in this. And in y directions, it's C minus signals in the nanoscale, in the same measurements, shows really high signal in this secondary arm. Especially, if, for example, if we have some organic materials and with some nitrogen contaminations, this also shows high. So this is urea, I think is urea, and organics is benzimidazole and cysteine benzimidazole. This shows very high C minus second arms. And for this is imerid pure nitrate, nitrate sulfate, and ammonium sulfate.
Imagine that you have a particle which has 0.4, 0.4, 0.4, somewhere in the middle. Would you think this is possible? Or
it's possible, yeah. Okay. If we measure mixed samples, it is possible. But we can use these second lines to corroborate this. Okay. So we can to evaluate how far they mix each other. So that makes sense. Yes.
Okay, next question, slide number 25. Yes, I was wondering, you show the deflection voltage.
Yeah.
And how high is your best mass resolution you can achieve? Because you say proxy AMU and the lines look very broad to me, but in reality, in terms of mass resolution, how high? What's the best you can get?
I think for this one, we can guess 10,000.
Okay.
So and they don't have much interference, so it's okay. We can show high lower. It's no problem. But more important for this mass peak, normally I got 4,000 and 5,000 because it's very low intensity. This I use the settings in the nanosims. It's a slits 2, and we got a flat peak. But we still show some shoulder effect from this. So we use them,
4,000, 10,000.
A calculated position in the left side from the center. So we can avoid this shoulder effect.
Okay, sure. Would you need much better resolution, or is it sufficient for your purposes?
This is the best I got, because we use the smaller slits, which may have the higher mass resolution. Okay. But we don't get the flat peak.
Okay. So, and if you were able to spend money on a better instrument, would you buy better resolution, or would you say this is sufficient for your delta 15, 14?
No, I don't think so. If we buy, no, because the reason not only come from the instrument, it's also come from the standard.
Okay.
Because the standard is soft and the direction is different. So.
Good answer. Okay. Yeah. Slide number 23, please. Go back. It's interesting to see that the errors are very different, very large at 60 plus and much smaller at 60 minus. Where do these errors come from, and why is there such a big difference?
The errors, in each pot, we measure in single pot, It's
Mhm.
each dot is each spot we spotted the sample.
Okay.
And the error mostly depends on how much counts we got from this
Counting
sample.
statistics. Okay.
So sometimes, for example, this NO2 minus, and especially you can see the Ce minus in this benzimidazole. I show last slides because these have really high signal.
I see.
So we can get 1 million counts.
Okay.
So the error is very small. And similarly for NO2 plus,
Mm.
NH4 plus, with the signal is really low.
So you would have to analyze different parts of the aerosol particle for getting smaller errors.
Yeah, yeah. One choice is we measure the same spot a long time, and another choice is we measure many spots and calculate them.
So two more small questions concerning the real life in the atmosphere. If you sample or if you get atmospheric aerosols, what is the largest range of delta N values you expect? What is the smallest you would expect to find, and what is the largest you would expect to find?
I read the paper. They also show some information about this difference.
Mm-hmm.
I have some. I think it's from compared to air, we can go to the value is minus 20 to 30, and the positive maybe is 10 to 15.
Okay.
So this is a large.
Okay. So last question, there's a publication which says they have a seasonal variation of isotope values going from minus 50 to plus 12.
Okay.
And they say it's changing from minus 50 to plus 12 throughout the year over the
Okay.
seasonal variation. My question, where do you think they perform their measurements? Or where do you think these aerosols are from on the planet? Is it the rainforest? Is it the Himalaya mountains?
I think it's for different from the season. It's secondary aerosols. It's chemical reactions in the atmosphere.
Yes.
Especially for these chemical reactions are not finished. This may cause the much higher isotope fractionation. So especially for different seasons, they have the different temperatures and different chemical compositions.
Okay.
So I think they don't finish every chemical
Okay.
reactions, the productant.
Well, I
So
can
they
tell
have
you the measurements were done in the Antarctic continent. They sampled aerosols from the Antarctic,
Okay.
and the lowest values were, as I say, minus 50. What do you think? Why are they so low? What could cause these low values?
I think the most important is for the temperature. It's the lower temperature, the mass isotope fractionation goes higher.
Mm-hmm.
So if we have maybe we measure some samples in tropical area, they have the high temperature,
Mm-hmm.
the 50 nitrogen and 240 nitrogen, they have the ratio is similar. But if we do these measurements in cold area, so this isotope fractionation rate goes really high. Yeah, it's
Okay, thank you.
So related to the last question, the isotope fractionation, is it just caused by gravity and density differences, or are there other effects?
is isotope fractionation comes from all the space, all the stage. It's temperature. It's more important the temperature. The temperature affects the chemical reaction. If we
Yeah, that bothers me a little bit. Is the isotope effect in terms of reactivity so big in 14 versus N15?
so
I would expect that the chemistry is nearly the same, but I'm not familiar
Yeah,
with
yeah, yeah,
the
comes,
species. But
across.
N14 and 15 look to me very similar in terms of
Mhm.
reactivity. So is there a big difference in chemical reactivity?
because they have the different mass.
Yeah.
Maybe the chemical cleaning in different molecules and the chemical reaction. They have the same speed. So they have the different energies. So for example, lighter isotopes may affect faster than the
Yeah, okay,
Heavy.
but we are talking 14 versus 15, so that's less than 7% or so in mass difference. So
Yeah.
that really shows up in the kinetic rates?
connected.
Kinetic rates of reaction, are there papers who've proven this?
Yeah. One is we can measure this outside from the atmosphere, another thing, we can do some measurements in the lab.
Yeah, that would be lovely, because atmosphere is very complicated usually.
Yeah, yeah.
Many chemical processes
Yeah, yeah,
going
yeah.
on simultaneously. So are there standard reactions with N14 or N15, and reactive rates have been compared?
Yeah.
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 I don't know, it's a question.
Okay, let me think about it. For example, the exchange reaction
Yeah.
for ammonium amino as NH4 plus in liquid
Yeah.
and NH3 gas in the air.
Yeah.
We can do these measurements in the lab.
Yeah.
So we can use different isotope ratio
Yeah.
in this container.
And
So-
has this been done?
Yeah. It's
okay.
Some papers already published this.
Okay, so that's my question.
Yeah,
basically.
yeah.
Okay.
So we can say for different temperature and different composition, this chemicals composition, they show the different isotope fractionation. For example, if we do this in 10 degrees and to 50 or 70 degrees, the isotope exchange reaction is different. Yeah. It's as I said before, in lower temperature they have a high isotope fractionation ratio.
Yeah, that's what I understand, because
Yeah,
there
yeah.
you may have density effects and so on.
Yeah.
But what I'm curious about is if you would make your chemical equilibrium, ammonia versus NH4 plus and NH3 for N40, and compare it at the same temperature with the equilibrium for N50. If you get a difference there in chemical rate also.
I don't see I understand your question.
I think you couldn't answer it. Basically, it's a question if someone has done this already.
Yeah,
so we
yeah,
could
it's,
discuss later.
For sulfate, there's a lot of experiments have been done, have been published.
Okay.
And for nitrate, I only saw the ammonium, NH4, as I
Okay.
said before. And for NOx reactions in the atmosphere, and for other species reaction, we don't find many these publications so far.
Okay.
Yeah.
So-
Especially in the atmosphere.
So there
chemistry.
may be chemical reaction differences, but there's certainly the gravity difference and things like that related to temperature and so on.
Yeah.
You've shown that noble metal surfaces play a different role for your resolution. For gold it works fine, for silver it doesn't. Any idea why?
I can show the slides first to you.